Morning, everybody, again, and actually good evening to our guest today, Duncan Forbes, who is in Australia at this moment. It is really a pleasure, Duncan, to have you as a speaker today. And to all our guest friends, let me briefly introduce Duncan. Duncan is a full professor at the Swinburne University of Technology in Melbourne, Australia, since 2005, and he's leading a team of students and postdocs researching formation and evolution of galaxies and their globular cluster systems. Duncan got his PhD at the University of Cambridge and has a long career with many awards and leadership roles at international research institutions and universities. I just mentioned he's been lecturer at the University of Birmingham, researcher at the Lick Observatories in Santa Cruz, and researcher assistant at Space Telescope Science Institute. He's been visiting professor at world-recognized institutions, including ESO. And very quickly, today, Duncan will present very recent developments about ultra-diffuse galaxies at their extreme. So, Duncan, the microphone is yours. I'll give you the time in 40 minutes.
Okay, thank you very much, Kelly. I'm just going to share my screen now. So, how does that look? All good?
Just a second. Right. Yes.
There we go. That's better. Okay. Thank you very much for the nice introduction, Kelly. Good morning, everyone. I wish I was there in person in Italy. Italy is one of my favorite countries, and I'm very much looking forward to returning in June of this year. So today I'd like to talk about ultra-diffuse galaxies, which, as you see, I've labeled galaxies at the extremes, and you'll see why. Most of the work I'm going to present today is under something called the AGATE project. So this is the analysis of galaxies at the extremes. It involves many colleagues in Australia, but also Anna Ferreira-Matal in Spain and Aaron Romanowski in the United States. And I'll also show a little bit later a few slides that results from the Vegas project, and that's deep imaging with the VST, and the Lewis project with deep MUSE data that Enrique is leading. So here's the talk outline. I'll go through some basic properties of ultra-diffuse galaxies. And then I want to talk about their globular cluster systems, because you'll find that they are some of the most interesting aspects of ultra-diffuse galaxies. And to do that, I'll go through 3 case studies, look at some galaxies in particular, and then try to talk about UDG formation in general, and wrap up and take some time for questions. So what is an ultra-diffuse galaxy? So there's a picture on the right there. You can see they're pretty featureless, but this image here is to scale. So you can see that the ultra-diffuse galaxy has a size that's comparable to the Andromeda galaxy. But if you were to count up all the stars in the ultra-diffuse galaxy, it has about the same stellar mass as that dwarf elliptical galaxy that you can see. So the 2 basic ideas for how an ultra-diffuse galaxy formed is maybe you started with a normal dwarf galaxy and you just puffed it up in size, or perhaps you started with a very large dark matter halo that would normally form a large galaxy like Andromeda, and in some ways that galaxy failed to form, and all you got was just a few stars forming. So those are the 2 sort of basic scenarios: a puffed up dwarf or a failed galaxy. So ultra-diffuse galaxies were discovered in 2015 using this type of telescope. This is the Dragonfly Array. So these are just an array of telephoto lenses. And that's Bob Abraham there, one of the developers of this Dragonfly telephoto array. Now, I say also rediscovered because there's a quote there from Sandage and Bengali, 1984. They found a new class of dwarfs of huge size and very low surface brightness in the Virgo cluster. So you might just argue that the Dragonfly Array just rediscovered these objects, but they found several hundred of them in total in the Coma cluster, and certainly rejuvenated this whole field. And there'll be a workshop on ultra diffuse galaxies up in Sesto in northern Italy in June. That's where I'm coming out. So here's the definition of ultra diffuse galaxies. I'm plotting here the effective size on the y-axis and the surface brightness, central G-band surface brightness. So the objects that Dragonfly discovered in Coma are all those red objects there. They define them to have a size greater than 1.5 kiloparsecs in terms of their effective radius, and surface brightnesses of less than 24. So they're very low surface brightness. And that corresponds to a stellar mass of around 10 to the 8. For the halo mass, I'll talk about that later. But the other things you can see on this plot are normal dwarf galaxies in the Virgo cluster. You can see a whole bunch of galaxies from the SDSS. And you see the size of the Milky Way disk there. So as I pointed out, the size of ultra diffuse galaxies is comparable to that of the Milky Way or Andromeda or some very large galaxy. Here's just another plot showing basically the same thing. You might be more familiar with looking at size against stellar mass. So here the ultra diffuse galaxies are those red objects. Again, stellar mass is about 10 to the 8, size is above 1.5 kiloparsecs. And there's one galaxy in the local group that comes pretty close to the definition of a UDG, and that's the WLM dwarf galaxy. But otherwise, we generally have to look further away to find ultra-diffuse galaxies. So here's their basic properties. They're very diffuse, they're very hard to study, but they're not actually rare. I'll show you a plot of that in a second. As you might see from those images, the first image I showed, they're pretty featureless. So when we normally study galaxies, we have a galaxy that might have a bulge, it might have a disk, it might have a bar. You've got none of those things in ultra-diffuse galaxies. The only features they do have are sometimes globular clusters and maybe a central nucleus, which could itself, of course, be another globular cluster. They're pretty well fit by a single Sirzik profile in terms of the surface brightness. We find them in clusters where they tend to be red in color and not have any gas, and also in the field where they tend to be blue and have some H1 gas. Their abundance scales with halo mass, and although some of them show some signs of tidal disruption, I think it's fair to say that that's rare. Most of them do not look like they're tidally interacting. Here's some examples of some ultra-diffuse galaxies. And so the top panel shows some red ones in the field and bottom panel some blue ones in the field. So it turns out about a quarter of the field UDGs are red and gas-free. So whatever model you decide to come up with to explain them, you have to explain that fact. So as I mentioned, they're not rare. This was done by a master's student of Enrico, looking at the Hydra 1 cluster using the Vegas deep imaging. And so that's that red point on this correlation here with all the other studies shown. So it shows the number of ultra-diffuse galaxies against halo mass. So you can see you've got a correlation there, a pretty good one, with a slope of roughly 1, so that you have a few ultra-diffuse galaxies in low-mass environments, but by the time you get up to clusters like Hydra or Coma, or the very large clusters, you can have hundreds or even thousands of ultra-diffuse galaxies. So that's why I say they're not rare. So here's some examples. Here's some HST imaging of 6 ultra-diffuse galaxies in the Coma cluster. And so all those little small white dots that you're seeing are globular clusters. I'm kind of assuming you know what a globular cluster is. It's a collection of 10 to the 5 or 10 to the 6 stars, a very compact structure. They're very robust. So even though they've all formed 12 gigayears ago, we can see them today like around the Milky Way because they managed to survive over cosmic time. So they're great traces. Anyway, these 6 here you can see are quite rich, if you like, in globular clusters. But there's also some that are globular cluster poor. So the UDG on the right, we think has no globular clusters at all. UDG on the left has 54 globular clusters, all those black spots. So how do we explain this difference? When we count up the globular clusters in UDGs, in this case on the y-axis, you count them up by mass. So that's the total mass of the globular cluster system on the y-axis, and the stellar mass of the host galaxy on the x-axis. And those dashed lines represent fractions that the globular cluster mass is a fraction of the stellar mass. So the UDGs in the coma cluster are the red symbols, and then there's a bunch of other galaxies on there, either green, which are dwarf galaxies in coma, or blue, local group galaxies. But the main point is the ultra diffuse galaxies have a higher fraction of mass in globular clusters compared to other dwarf galaxies for the same stellar mass. The plot also shows where the Milky Way lies on this plot. So it has a percentage of mass in globular clusters relative to the mass of the Milky Way halo of about 1%. So we can get up to about 10% in ultra diffuse galaxies. Another interesting property is the relationship between the number of globular clusters and the halo mass. Now, this correlation, which the observations here are the red points, is for normal galaxies. It seems to cover all different types of galaxy, and as you can see, it covers over a very large range of virial mass. But what we don't know is whether this relation holds for ultra diffuse galaxies or not. But if it does, we can do something like this. So there's, if we have 20 globular clusters, we can essentially just read off or predict the halo mass, right? It's obviously very difficult to measure the halo mass of a galaxy, but if this correlation holds, it's fantastic. We just have to count up the globular clusters, read off the halo mass. So what evidence do we have that that might be true? This is a plot where the observations come from my student, Jonah Gannon. Little black dots are simulations, lustrous TNG 100. So on the left-hand axis, that's just simply the number of globular clusters, and an arbitrary line is being drawn across at 20, which on the right-hand axis corresponds to 10 to the 11 in terms of the halo mass of the galaxy. And then 3 panels just show the size of all the galaxies that we observed, the velocity dispersion that we measured, in this case using AGATE telescope, and KTWY, which is the equivalent of MUSE and VLT, and then the dynamical mass. So that's just sigma squared r, so that's the enclosed dynamical mass. And I think you can see there's a correlation there between the dynamical mass that we measure and the number of globular clusters in a galaxy. So I'll just put a little line on there. So that gives us some confidence that indeed we have larger total halo masses in galaxies that have more globular clusters, more UDGs. So maybe that relation does hold. So assuming that the globular cluster number halo mass relation holds, let's look at the pretty famous stellar mass halo mass relation. So that black line there is just a standard relation. I think this is from Ben Ruzi, 2013. Symbols are the same as the plot I showed you before. Again, the red symbols are the ultra diffuse galaxies in the coma cluster, and you can see they sit quite a way off the 1 sigma of that relation out to very high halo masses, kind of suggesting that they have overly massive halos. Just going to sort of divert a little bit into simulations. What can they do, tell us, and how good are they? So this is the illustrious TNG simulation. So first of all, look at the right panel. This is the non-UDG. So the red lines here is basically that scaling relation from my paper, Burkett and Forbes. And the little black dots are the illustrious simulations. So I think you can see pretty clearly that they can't reproduce the relation for normal galaxies. So perhaps it's no surprise on the left-hand side that there's no relation for ultra-diffuse galaxies either. So I'm afraid the simulation probably doesn't model globular clusters correctly. Here's another simulation where they tried to simulate ultra-diffuse galaxies in Romulus C. That's the orange points. So they get a bunch of galaxies with what look like the right sizes and right stellar masses. However, compare this to the Fornax cluster, which are the green points, and you can see that the simulation only produces ultra-diffuse galaxies and no regular dwarf galaxies. So that's a problem. So it could be something to do with spurious disk heating that's puffed up these galaxies artificially. So I'm not sure we can use that simulation either. Here again is Romulus C, and now just back to that stellar mass halo mass relation. All their ultra-diffuse galaxies are either following the standard relation of, say, Ben-Ruzi, or they lie to the left, which is due to tidal stripping. None of them are found on the right-hand side with overly massive halos. So again, that's a problem. So I'm going to turn now to Rosetta Stones case studies. But of course, as you know, Rosetta Stones sometimes turn out to be pet rocks. Well, let's find out. So here's the Vegas discovery image of UDG1 in the 5846 group. So this is very deep imaging with the VST telescope, Omega Cam. So that's the ultra diffuse galaxy in the center there, and some globular clusters associated with it. After this, HST looked at the same target. So here's the HST image. Very nice. And I'll just zoom in and turn the globular clusters into black. So here you can see the globular clusters quite clearly around this ultra diffuse galaxy. The original paper, we estimated 45 globular clusters. Muller in 21 estimated 26, but now with this deeper data from Danieli that I'm showing you here, the number is now 54. And 54 globular clusters, if you put it into that scaling relation, would imply a total halo mass of 3 by 10 to the 11. So here's some other properties of this ultra diffuse galaxy. It's perhaps the best one studied. So again, from Danieli's work, it's got a globular cluster luminosity function that is essentially equal to the universal one. It peaks at a V-band Johnson magnitude of -7.5, has basically the standard width. They measured the size of the globular cluster system relative to the effective radius of the galaxy, and that's that number of 0.8. So the globular clusters are roughly the same, extended as much as the galaxy's starlight. And then, as I said, the number of globular clusters is 54. That converts into a specific frequency of 78, or if you prefer to write it as the mass of the globular cluster system divided by the stellar mass, that's actually up at 13%. So that's enormous, especially when you consider that the original mass of globular clusters in this galaxy could have been even higher. Here's what it looks like on a stellar mass halo mass relation. So again, you've got some standard relations, you've got some colored points showing various models, and that cyan data point shows where NGC 5846 UDG1 lies, well off the standard relation, suggesting an overly massive halo. Here's some properties about its stellar populations. It's just very recently just been measured by a few works. So you can see generally that it's old, relatively metal poor. Perhaps one of the most interesting things is the study by Muller that finds the stars and the globular clusters to have consistent ages and metallicities. So they both seem to have formed at the same time, roughly redshift 3, from the same enriched gas. As I mentioned, the ratio of globular cluster to star mass is 13%, but if you allow for some globular cluster destruction, your conclusion is that almost all the stars that you see in this galaxy were originally in globular clusters, just like we think a large fraction of the halo of the Milky Way was originally in globular clusters. So the halo mass, 3 by 10 to the 11, stellar mass is 10 to the 8. This could be a good candidate for a so-called failed galaxy. Here's what's coming up in the near future. I have a student working on some Keck KCWI integral field unit data of this galaxy. So we're trying to get some more velocities of globular clusters and measure its dynamical mass. So that's coming. So I just wanted to expand a little bit about failed galaxies. This is sort of it's more a picture rather than a model. So what we're envisaging here is that redshift 3, we have lots of globular clusters forming, and then we need some form of self-quenching or perhaps infall into a cluster at very early times. So lots of globular clusters form and maybe a small number of stars. However, some quenching process stops more star formation. Over time, globular clusters are disrupted, and that leads to more galaxy stars. So you might expect globular clusters and stars to have the same old age and low metallicity, that the globular cluster system in the galaxy has about the same size. You get a large fraction of the stellar masses in these globular clusters, and its globular cluster-rich galaxies lie in massive dark matter halos. And those all seem to be the properties for 5846 that I mentioned. I'll just turn to another case study. So this is DF44 in the Coma cluster. It also has lots of globular clusters. But in this case, we spent a lot of Keck time trying to measure a kinematic profile. So the kinematics that we measured, the velocity dispersion is a function of radius. So that is radius in kiloparsecs on the x-axis. That's the black points. So you'll see those black data points are the same in each plot. And on the left, we're trying some models that fit an NFW dark matter profile, which is a cuspy profile. And then on the right, we're fitting a so-called Dicentio profile, which has a core in the mass profile. I think the thing to focus in is just focus on the green line on the right-hand side, and you'll see that a 10 to the 11 solar mass cored dark matter profile does a pretty good job of reproducing the observed velocity dispersion profile. I'll just point out this galaxy has no sign of rotation as well. So that's what the kinematics point to, and this is the only ultra-diffuse galaxy that has extended kinematics like this to be able to infer its total halo mass, to measure its total halo mass independently of its globular cluster count. And now just return to this plot, and if you look, that blue symbol, the dark blue symbol right in the middle is where DF44 lies. It has roughly 80 globular clusters, and there's the halo mass of 10 to the 11 that we measured from its kinematics, and it fits right on the relation, or within the scatter at least. So I think we have at least one UDG that fits this relation. Next case I want to talk about is DF2. This is in the 1052 group. It has a velocity dispersion of the stars measured. It's very low, 8.5 kilometers a second, and a velocity dispersion of the globular cluster system, which is 7.8. So very low dynamical mass relative to its stellar mass, and hence it has little or no dark matter. So here's a plot that from Gannon 21. So it looks at the mass to light ratio. So that's a dynamical mass divided by the luminosity of the galaxy as a function of dynamical mass. So those little black dots you see are just normal galaxies. So there's a U shape there ranging from normal dwarf galaxies all the way up to giant galaxies. The colored symbols show the ultra diffuse galaxies that we have dynamics for. So the two in the lower left is DF2, the blue point, and DF4. So both of these are in the 1052 group. Both of them seem to have very low velocity dispersions, very low dynamical masses and basically little or no evidence for dark matter at all. Whereas the other ones, all the other UDGs, sit above the U shape, suggesting very high dark matter fractions. So we seem to have this huge diversity in the dark matter halo properties of ultra-diffuse galaxies. One other interesting feature about DF2 and DF4 is when you look at its star clusters, this is what the luminosity function looks like. You see some objects which look consistent with being globular clusters. So that dotted line shows you the universal globular cluster luminosity function, peaking at -7.5. So you seem to have a few of those, but you also seem to have a whole bunch of more massive, more luminous globular clusters. They could, in fact, be something that we call ultra-compact dwarfs. They look very much like a globular cluster, but they just have these higher luminosities. In fact, I've got a picture here. So here's a HST image in the halo of M87. And so basically, the brightest sort of white dots that you can see in this image are just sort of normal globular clusters. But the bluish ones that look larger in size are what we might call ultra-compact dwarfs. And so M87 has a whole bunch of these ultra-compact dwarfs, as well as the normal globular clusters, and bizarrely in DF2 and DF4, they also seem to have a lot of these ultra-compact dwarfs. And we don't really understand why, but any theory that could try to explain why those galaxies are essentially dark matter free should also try to explain why it has this population of these ultra-compact dwarfs. So put all these galaxies onto this stellar mass halo mass relation now. So there's NGC 5846, UDG 1, the ellipse above it is DF44, and out to the left, the cyan way off the plot, is DF2 and DF4. So sometimes too much halo, sometimes not enough perhaps, but anyway, it seems, as I said, of a great diversity in the properties of halos of ultra-diffuse galaxies. So what could explain this? Well, the easy way to go to the left is tidal stripping. If you wanted to introduce warm dark matter, that would also take you in that direction. In terms of sort of theory, higher concentration halos or earlier forming halos would be out the left in this plot. Conversely, lower concentration and later forming halos would be out on the right. I'd also like to point out that in some cases, we see other reasons for ultra-diffuse galaxies forming. As I said, some of them clearly are interacting, and in this case, it's a nice spectacular Vegas imaging from the Hydra 1 cluster showing that UDG circled there that could be related to this to the tails that are coming out of these two galaxies in the Hydra 1 cluster, and that may have led to the formation of what we classify as an ultra-diffuse galaxy. I haven't mentioned much about stellar populations, just to say, this is from my student, Louisa Buzo, that we found field UDGs to have younger ages than cluster UDGs on average. And on the right-hand side, when we coded it by globular cluster poor or globular cluster rich, you can see that the globular cluster rich ones have lower metallicity. And that's seen again in this next plot. So this is just showing metallicity against stellar mass. You can see some relations there for local galaxies from Kirby, Simon, Galatsi. But the interesting thing is the globular cluster rich galaxies, which are the red symbols, lie off the relation and are systematically much lower than the globular cluster poor ones. In fact, well, they are at metallicities that are similar to globular clusters themselves. Now, the age metallicity relation, of course, evolves with redshift. So here I've just put on the relation for a redshift of 2, and interestingly, it seems to fall pretty much through the globular cluster-rich ultra-diffuse galaxies. So one interpretation could be that they formed around redshift 2, and that's where this, the metallicity was set. So these, again, could be candidates for failed galaxies. I just want to say briefly what sort of a standard model might suggest for dwarf galaxies that have lots of globular clusters is this kind of picture here, with a couple of references. So a dwarf galaxy falls into a cluster. The earlier it falls in, the fewer additional stars form, so that you end up with a dwarf galaxy with a very high globular cluster to star ratio. So we might expect the globular cluster-rich galaxies to be located at the inner parts of clusters. So this diagram, sometimes we call it an infill diagnostic or a phase-space diagram, shows the velocity of a galaxy relative to the cluster center as a function of the virial radius. And there are ultra-diffuse galaxies from 3 different clusters here: Coma, Perseus, and Hydra, with the Hydra data just coming, which is hot off the press from Muse. Each symbol is coded whether it's globular cluster rich, having more than 20, globular cluster poor, less than 20, or in some cases we just don't know what its globular clusters, how many it has. And this diagram is divided up into the infall time. So basically everything in the black zone fell into the cluster a very, very long time ago, at least more than 6.5 gigayears ago. And so, as I said, we might expect that region to be occupied by globular cluster rich UDGs, and that does not seem to be the case. In fact, if anything, the trend looks like it's the opposite, that it's actually globular cluster poor UDGs that are occupying the inner parts of a cluster. So certainly would like to get more statistics on this, but that's the direction that this is going. So just to wrap up, on the simulation side, UDGs were not predicted to exist originally in simulations. Some simulations are trying now, and I would say that they need to reproduce the well-known relations for normal galaxies first, so that includes size and mass, and also globular cluster number versus halo mass relations. And the UDGs that do occur in simulations only seem to be the normal ones, or perhaps the undermassive halo ones, but they cannot reproduce the overly massive halo UDGs. And any process that you can think of that you want to make red ones, old and passive cluster UDGs, you must also account for that 25% of field UDGs that are also look like they're red, old, and passive. You've probably got the idea that simulating globular clusters and understanding globular clusters is the key here. But once we do solve that, I think that insight will lead us to new galaxy formation physics. So in conclusions, ultra-diffuse galaxies, we select them in size and surface brightness space, are certainly a mixed bag of objects. So there's bound to be different formation pathways. Some or most could be large-sized dwarfs, but some of them appear more like what I've described as a failed galaxy. Understanding their globular cluster systems are going to be key. And that ranges from some galaxies that have none at all to others that have many tens of globular clusters. So you can probably see why I've called UDGs galaxies at the extreme, and they offer the potential for new insights into the process of galaxy formation. Thank you for listening.
Thank you, Duncan. It was really, let me see.
How are we doing? Got back to you.
Yeah. So thanks again. It was really great and interesting, a lot for me.
Thank you.
Thanks also for being very much on time, actually. So
perfect. It's hard to tell sometimes, yeah.
We have questions. Please unmute yourself. And I see the first hand raised by Piero. Please, Piero, speak up.
Hello, hello, Duncan. Thanks a lot, first of all, for the great talk.
Thank you.
So I have a pair of questions. So first of all, I just want to say that I'm a planetary geologist, so I'm a bit out of this field. So I hope that my question doesn't look weird. But anyway, I wanted to understand a little bit better what is the main, what can diffuse galaxies, the ultra diffuse galaxies, tell us about in the big frame, let's say, so about the formation of how the universe works anyway.
Yeah, well, some of the plots that I showed you were of the stellar mass halo mass relation. So that was the mass of stars in a galaxy and the dark matter halo. And these are probably the two most fundamental quantities for a galaxy, right? You know, we think that the way galaxies formed is they formed in dark matter halos, gas condenses and forms some stars and so on. So, you know, you saw we have a pretty good relationship between stellar mass and halo mass, and there's a standard relation, and basically all of our galaxies lie on that relation. Everything that goes into a cosmological simulation falls on that standard relation. It's often an input. So when I start to find galaxies that deviate from the standard relation with, you know, out both directions, you know, it's time to get worried, or at least you want to understand, you know, why that's the case. And when you do understand it, then that's some physics that I think that you can put back into your cosmological models and do a better job of reproducing galaxies.
Okay, thanks a lot. And then I have another question, because I have seen that the globular clusters lack dark matter, basically, or are supposed to have very little dark matter. So how can we explain that? I mean, and what does it tell us, this lack of dark matter?
Yeah. So when we look at the globular clusters of the Milky Way, because they're the best studied, there is basically no evidence for any dark matter in an individual globular cluster. Okay, so they're on a size scale of, you know, 10 to a million stars. We think that it's completely stars. There's no dark matter. However, those globular clusters are in a halo around a galaxy, and that halo around the galaxy contains dark matter. Usually, that's the standard idea. And I guess what I've been showing you today is there are some ultra diffuse galaxies that have a lot of dark matter, a very massive halo, but there were a couple of galaxies that seem to have no dark matter, right? So as well as you started out correctly, globular clusters themselves don't have dark matter, but we usually think that all galaxies do. And so it's really interesting if you've got a couple of galaxies at least that do not seem to have dark matter in their halo. Again, don't know why.
Okay, thanks a lot.
Sure.
Other questions? So then can I have some? Okay, actually, okay, we have Mauro, but let me anticipate with one simple. Maybe it's a comment I ask you now, Duncan. It's so we know you showed it very clearly that UDGs are so diverse from each other. But what I find, I mean, and you know, in all the scenarios there are several possible formation scenarios, and you know, everything kind of, you can make sense of everything with some approach or the other approach to explain the behavior. What I find really annoying is the globular cluster luminosity function of those DF2 and DF4. This is something that really puzzles me, because you know, the behavior, it's really, that's something that I can't really fix that behavior in one of the possible scenarios. Yeah, you already commented at that. I don't know if you want to extend a bit more.
Yeah, no, I think you're right. It's very curious. So of course, you know, the study of those two ultra diffuse galaxies has largely been by Peter van Dokkum and collaborators, and he's also come up with a model that he tries to explain both the dark matter deficiency and the very massive star clusters, and he calls it a bullet dwarf scenario, where about 8 giga-years ago, you had a very high-speed collision. So that compressed the gas and led to very large star cluster formation, and then it led to a chain of galaxies actually in that group, where the dark matter deficient ones are at the ends. And of course, that's quite controversial and needs testing and so on. But the nice thing about it is it does make some predictions that are all being tested, now by various groups. You've probably heard of the bullet cluster, where two clusters of galaxies, went through each other, and so it's the same kind of process, but at a smaller scale. Yeah, I agree with you. It's pretty weird, and so you would really like one model to explain both the dark matter deficiency and the massive star clusters.
Right. Thanks, Mauro.
Oh yes, thank you, Duncan, for your very nice presentation. Me neither. I'm not an expert in this field, so sorry for my question. But looking at these ultra diffuse galaxies as a very low density aggregation of stars that should not be existing, as far as I understood, because they could not sustain by self-gravity. I thought to a similar phenomenon, which is the Trojans asteroids in the solar system. They are grouped in around the Lagrangian point, and they are not grouped by their self-gravity. So my question is, sorry for this stupid question, inside the galaxy cluster, that could be Lagrangian points where stars can concentrate, even not sustaining by their self-gravity. Thank you.
Okay, sure. I mean, I think in the case of ultra diffuse galaxies, they are self-gravitating systems. We do see, we knew of low surface brightness galaxies or low stellar density galaxies for a long time. In the case of ultra diffuse galaxies, you would expect them to be quite fragile and easily broken up in a cluster environment by all the other galaxies and the motions. So again, one of the arguments very early on when they were discovered is that they must sit inside dark matter halos, massive dark matter halos, in order to protect them from these interactions. So yes, I think, so maybe it's not too surprising that we infer some massive dark matter halos in some of these ultra diffuse galaxies, just to keep them intact and not have them all showing signs of being tidally disrupted. Thanks for your question.
Okay, thank you again.
Other questions for Duncan? So, if not, thanks, Duncan, again for waiting till this late today for your webinar to us. It was really a pleasure and very instructive too. Thanks a lot. And hope to see you soon. I will not be in Sesto, but I know that many of us will be there. Some of us will be there. So thanks and have a nice evening.
All right. Thank you very much for inviting me, Kelly. I think it's time for a glass of wine.
We're going to have
Thank you, Daniel.
some coffee.
Yeah. Bye.
Ciao.
Thank you. Bye.
Thank you. Start registration.
Goodbye.